Now really, this simplification works on just one principle. It's just one little principle, and you guys have seen this for a long time. In fact, you've simplified radicals before. We're just going to make them, of course, a little bit more advanced for this class. Simplifying radicals works on one little rule. It's called the product rule for radicals. And here it is. It says if you have a square root of a times b, a square root can be broken up. The product can be broken up. For instance, if I have the square root of a times b, that comes down to the square root of a times the square root of b. In fact, I showed you that before. In fact, I've previewed this section before in section 10.1. I kind of told you what we're going to do already in this section. But this lets you solve or simplify a lot of these radicals. I'm going to put this a little bit, well, I'll give you an example first to prove that it's true by one example. Then I'll make this in general for you. So here's a little quasi-proof. If I have the square root of 36, I know the square root of 36 is, well, that's 9 times 4, right? You follow me? According to this product rule, I should be able to separate the square root of 9 times the square root of 4. How much is the square root of 9?
3.
How much is the square root of 4?
2.
And that is equal to, how much is the square root of 36? It does work. Okay, so if we can break up some number or some quantity as a product, I can split that radical up, do each of the radicals individually, and multiply their results, so those products. And that will give me the same answer as if I would have done it normally. Are you following this? Now, not only does this work for square roots, this works for any type of root. Just don't forget the end. A lot of people lose the end. Whatever that power is, or whatever the root is, you got to keep that root. Also, I need you to know that this works both ways here. If I have the square root of 2 times the square root of 7, can I multiply those roots together? Well, that's what this says as well. It says if I have an nth root times an nth root, I can put them under the same nth root. Does that make sense? Okay, so let's try it. If I have a square root of 2 times a square root of 7, what type of root am I going to get?
Square root of 13.
Still a square root. Sure, it says the same root, doesn't it? Same root. And then what do I do with the 2 and the 7?
2 times 7.
So that's a square root of 14. That works. We can put some roots together as well. How about that one? Are these roots able to be put together? Can we put those things under the same root?
Yeah.
What lets you know that?
If the root is able.
Okay, so let me ask you a question. If I had this, could I do it?
No.
No, that's not what it says. It says the ends have to be the same. So what we're looking for when we're combining our roots, we're looking to see if we first have the same root, and then we're going to multiply the radicands, whatever's inside them. So what type of root are we going to have, ladies and gentlemen?
4th root.
4th root of?
6. Times 3x squared.
Good. How much is 6 times 3x squared?
18x.
Okay.
25.
Is there anything I can do to simplify that the rest of the way down? Let's see. Can you think of a fourth root that divides 18? Can you think of that?
No.
I can think of a square root. I can think of, I'm sorry, perfect square. I think of 9, but that you can't find the fourth root of 9. Find the square root of 9. We're doing the fourth root. We'll deal with how to simplify that in just a little bit. Let's try one more for today, and then I think we'll be done. Does it still work? Fractions. Can I put together some roots if they're fractions?
Yeah.
Can I put together these roots? What do you think?
Yeah.
They're both square. Okay, so if I put them together, I'm just going to have the square root of 3 over x times y over 2. When you're multiplying those fractions, you would check for anything that you can simplify. Can I simplify anything in this expression?
No.
No, so we're going to have just a square root of 3y over 2x. That's as far as we can go. Raise your hand if you feel okay with this so far. We talked about it. All right, next time we'll talk about the quotient rule. I'll show you how to simplify radicals in general. That'll be a good day. Well, I guess it'll be on Wednesday. So last time we were talking about the product rule for radicals, and we said that no matter what our root is, if we have the product as a radicand, we can split up that root as a product of two roots, or any nth root. That doesn't really matter. Square roots, cube roots, fourth roots, anything. What we're going to talk about today is the quotient rule and then how to apply these things to any radical, and we're going to be able to simplify them. So the quotient rule says something very similar to this product rule. It says if instead of a product you have a quotient inside of any nth root, similar to our product rule, we can break that thing up. We can do nth root of the numerator over nth root of the denominator. And that's legal too. So products and quotients we can both break up. For example, if you have something like this, a square root or any other type of root for that matter, let's say it's a square root this time of 9/20. All this says is as long as we take the root of the numerator and the root of the denominator, both of them, we'll be okay. So here we'd have the square root of 9 over the square root of 25. Just let's simplify this expression. How much is square root of 9 over square root of 25? Or say the square root of y over 36. Now, when we do split this up, we could do the square root of y, for sure, and the square root of 36. Now, while we can't simplify the square root of y, we can simplify the square root of 36. So not all the time are you going to be able to simplify both the numerator and denominator, but maybe one of them you can to make this thing a little bit easier. Which one? What are we going to have when we simplify the square root of y over the square root of 36?
Square root of y over 6.
Good. So the square root of y, nothing happens. Square root of 6, or sorry, square root of 36 gives you 6. So in one case we have a square root, in the other case we don't. That's legal. It's okay. We can have a square root on the top or the bottom, numerator, denominator. This also works with any other type of root that we have. So for instance, if we have, say, a cube root, it's still legal to split those up. I said for any nth root, so it doesn't really matter what our root is as long as we keep the same process. So in the square root of the cube root of 27/64, we just got to make sure we keep that a cube root and don't, misinterpret that as a 5. Let's practice one more and then we'll learn how to simplify this in any context. Let's practice with fifth root. Of 7 over 32x to the fifth. First thing we know is that any type of root we can separate a quotient. That's the quotient rule for us. So we're going to have a fifth root number. How about the x to the fifth? Can you simplify a fifth root of x to the fifth? Yep. How much did I give you? Yx. How does it cancel out? What are we doing when we're counting? So as long as we have this, we're done. That's as far as we go as far as simplifying our combination of these two rules. We'll be using the product rule and the quotient rule. So this really, it's our bread and butter for this particular section. We're going to be using this almost constantly, in combination with the idea of this one. Remember how I showed you 2 ways to do that, as a matter of fact? A long time ago, I previewed this information. We're going to be using the second way to simplify these roots. All right, here's our goal ultimately. The goal for simplifying radicals, which we're going to do right now, what we're going to be doing is looking for perfect nth roots. So it depends on what type of root you have, what you're looking for inside of your radicand. So if we have a square root, we're going to be looking for perfect squares. If we have a cube root, we're going to look for perfect cubes. If we have a fourth root, we're looking for perfect fourth powers. So what we're looking for when we're simplifying radicals are perfect nth roots. I misspoke there, perfect nth numbers, like square numbers or cube numbers. Let's do a couple basic examples. We're going to start with just some numbers, just practicing simplifying these things. So let's go ahead and do this. Remember this process, I asked you some square roots. You guys were pretty good at that. Square root of 64 is, hopefully not. Square root of 81. Square root of 25. Square root of 144. Of 196. Square root, yeah, 14. Square root of 169 is 13. Square root of 196, reverse is 14. That's kind of cool, right? Square root of 225? Just go one higher. 15, very good. All right, well, we got the hang of this, right? 14.7, I don't know what it is. No, it's 15. Square root of 36. Okay, that's 6. Now, when we say the square root of 18, can you do that?
No.
You can't give a whole number answer for it. However, using this idea, we're going to be able to simplify it to make it at least a little bit smaller inside of our radical. That's the goal. I'm sorry, what type of root do we have here? If we have a square root, here's our goal, ladies and gentlemen. We're going to be looking for perfect nth numbers. So if I have a square root, I'm going to be looking for perfect square numbers. Here's how you think of this, and you've done this before. It's just that should be a little bit of review here. You just haven't dealt with the variable portion, which I'm going to add on in just a bit. If you have a square root of 18, we need to look for a perfect square number, which you guys just listed out for me when we were just talking about this 30 seconds ago, that divides 18. So for instance, can you think of a number that you can take the square root of that divides 18? 9 works. You can take the square root of 9, right? Do I want 6 and 3? Why wouldn't 6 and 3 work? Because a lot of people go, oh yeah, just find two numbers and multiply. Can you take the square root of 6? Can you take the square root of 3? Then why would you use those numbers? What we're doing is using numbers that you can take, at least one of them, you can take the square root of. Probably only one of them you can take the square root of, otherwise you can just take the square root number at the beginning. Because we're going to be using this, one of these things, and we need to be able to take the square root or that type of root of one of those numbers. So if we're dealing with a square root, we're looking for a number that you can take the perfect square of, that's a perfect square number, that divides 18, because we're going to split that up. So instead of 18, you told me 9 times 2. So I'm going to write this, I'm going to write the number I can take the square root of first. 9 times 2. You agree that's 18, right? Okay. You see, now that we have this, a product, we can use the product rule, which says if you have a product of a number inside a radical, I can split that up as two different radicals being multiplied together. So instead of square root of 9 times 2, this says I can do the square root of 9 times the square root of 2. Do you see that that's legal? Math legal. Yeah, don't get thrown in math jail for doing that, that's fine. Can you take the square root of 2? Can you do that? Square root of 2 is, I don't know, 1.41 something forever. I don't know exactly what it is. Can you take the square root of 9?
Okay.
Well, that's great, because this at least lets us simplify part of our radical. So if you can take the square, what's the square root of 9? This is 3. This was, we can't change that at all. That stays there. So here's the idea. If you have the square root of 18 over here, which is some number, we're going to break that number up into a perfect square times something else. We split that up as two different roots. And then hopefully, if you've done this right, you'll be able to take the root of one of them. If we can take the square root of 9, that's 3. This is a multiplication, that's a multiplication. The square root of 2, I couldn't do anything with that, so it just stays there. So instead of the square root of 18, I have 3 root 2. Is this a little bit easier to deal with? Yeah, in a math problem it will be. It's a smaller number inside of a radical, that's kind of nice. Plus, in order to add and subtract radicals, which we're going to do in the next section, you have to have them in the simplest form. That's in the simplest form. I think we'll feel okay with this so far. Okay, we're going to try some more examples here before we add some variables in there. Okay, I want you to think on it. Don't say it out loud right now. Think on it. First thing you got to do is think of the type of root we have. What type of root do we have?
Square.
Square root. So you're looking for a perfect square number that divides 98. Don't say it out loud. I want people thinking on this, okay? Think on a number that divides 98. Now, you only have a few numbers to choose from, right? So you can take the square root of 40. Square root of 49, of course, the square root implied that those things are square root of 32. Now, clearly we have a square root. We've got a square numbers. That's why we're choosing numbers like 16. That's why we're choosing numbers like 9. Okay, we just say the square root of 14. All right,
No,
that's
we
it.
go 14 times 1.
Sure, but the square root of 1 just gives you 1 over and over again. So it's actually not breaking that down any. Right? I mean, square root of 14, you stay square root of 14. Square root of 1 is 1. You still get square root of 14 back again. That's a good point. But yeah, we're looking for numbers besides 1. Ooh, should we be looking for perfect squares anymore? What do you think?
No.
For instance, the number 4. Is 4 going to help us in this case? 4 times 10.
No.
Can you take the cube root of 4? Cube root of 10? So okay, don't say it out loud. I want you to think on this. I want you to think about it. Firstly, I want you to think about what type of numbers you should be looking for. Should we be looking for perfect squares or perfect cubes? What do you think?
Cubes.
Sure, perfect cubes. So think in your head, about a perfect cube that divides 54, just in your head. Again, the perfect cube numbers are 8, 27, 64. That's it. It's only 3 you have to choose from here. By the way, is 9 going to work? Should you be putting another one? We'll have the cube root of 27 times the cube root of 2. Cube root of 2, we're done with that. We can't simplify that anymore. But the cube root of 27 gives us how much? Everybody. That wasn't everybody. You got lazy today. Come on. Play along. Have fun. Yeah, this gives us 3. Then we have a cube root of 2. That's as simple as we can make it. Cube root 54 gives us 3, cube root 2. Would you raise your hand feel okay with this so far? That row? Yes, no? Okay, good. Square root, not a cube root anymore, square root. I can split that up by the product rule because any nth root I can do that. So square root 81 here, 81. What I look for is, I'm sorry, perfect what's here? Squares. So powers of 2. Here's the point. If I have x to the 5th, like I have y to the 5th here, I can write this a lot of different ways. I could choose to write this as, that's true, isn't it?
Yeah.
Sure. Or this one. That's true, right? Or I could do that one. That's true. Or I could do this. Is that still x to the 5th?
Yeah.
Now what we're trying to do is write this with as many power 2s as we can. Would you agree that this way is giving us as many power 2s as I can?
Yeah.
Here I don't have any. Here I have 1. That's great. But this one, That's not so good. This one isn't giving it any power 2s. That's not good at all. This is the most power 2s I can find. Now, why I'm looking for power 2s, and I showed you this earlier as just a review at this point, is whenever we have a power 2 matching with a square root, or whenever the power matches the root, I can take out one of those x's outside of my radical. It simplifies. A square root and square root do each other. So since I have a square root, I'm looking for x to the power 2 in this case. I hope you remember that we've done this already at least a couple times. I'll keep the square root of 81 because I don't need to break that number up anymore, such as 18 or 98. That's already a perfect square, so I don't need to split that up. If you take the square root of it, leave it alone. But at y to the fifth, instead of leaving it y to the fifth, I'm going to write this as y squared times y. As many y squared as I can, but I still need y to the fifth. So I can't just leave it y squared times y squared because that's y to the fourth, I need y to the fifth. Raise your hand if you're okay on this so far. Good, all right, that's good. Now let's see what happens here. Can you tell me what's the square root of 81?
9.
So I'm going to cross that out and put a 9 because I just took the square root of it. That means I pull it outside of my radical. Are you following me here? Can you tell me what's the square root of y squared? Remember, what we could do, why this whole process works, I'll show this to you here. Because of our product property, you could do the square root of 81 times the square root of y squared times the square root of y squared times the square root of y. Do you see that that's the same thing we're doing right here? Nudge me if you're with me. You have to kind of get this part. Are you okay that what I just did is what we did here, what we did here, what we did there? Yes, no? I can split that up by the product rule because any nth root I can do that. So square root of 81, square root of y squared, square root of y squared, square root of y. Why am I choosing the y squared here instead of like y to the third or y to the fourth? Well, it's because I can take a square root with a square and cross it out and simplify it. Now we can say, okay, what's the square root of 81? Oh, that's 9. What's the square root of y squared, folks? Good. Because we know those simplified. What's the square root of y squared?
1.
What's the square root of y?
It's the square root.
Can I do it? Can I simplify it at all? I'll give you a little, actually a big hint. If the power is bigger than or equal to the root, you can simplify it. If the power is less than the root, you can't. Why?
You can break it down anymore.
You can't break it down anymore, that's right. If the power is less than the root, that's power 1. I can't write that as a power 2 times something, right? If it's equal to it, I can simplify it. If it's greater than it, I can write it as a product of those powers put together. Does that make sense? So if it's bigger than the root, simplify it, or equal to the root, simplify it. If it's less than, you're done. You can't simplify that. So in our case here, we cannot simplify the square root of y. I'm just going to leave that square root of y. Now, can I write this any simpler than this?
9y squared.
Sure, yeah, let's put those y's together. Really don't need these because if I write it like this, it's implied that we do have multiplication. That's as good as I can make it. That's completely simplified. You okay?
Yep.
Can you get directly from here to here without showing this step? Sure, you can do that. Or actually here to here, here to here. Point right correctly. This one to this one. Sure, you could. You can do 9. This gives you a y outside your radical. This gives you a y outside your radical. But this one, you wouldn't be able to cross that out, would you? Doesn't match. It stays inside your radical. That's the way you do this. Let's try a few more here. See, we're having fun now, right? Don't we love? I loved crossing things out when I was your age. Although maybe I'm not some of your age yet.
Am I older than you?
That'd be awesome. Although maybe I'm not some of your age yet.
Am I older than you?
That'd be awesome. See, when I taught high school, I was always the oldest one in the room. It sucked. I felt they all thought I was 50.
Oh.
Yeah, they did. I was 24 at the time when I started teaching high school. They're like, you're old, huh? I got brothers. I was 24 at the time when I started teaching high school. They're like, you're old, huh? I got brothers like old as you. And so the ones who actually had brothers and sisters of my age were like, okay, yeah, I know how old he is. But some were like, what are you, like 40? 40. They failed. They failed. Some were like, what are you, like 40? 40. They failed. They failed.
And that's why you started teaching college.
No comment. Okay, cube root 24, a to the 9th, b to the 4th. What we need to do is write this as perfect, whatever type of numbers we need to simplify this. So what type of root do we have? We're looking for perfect cube numbers then. What we deal with is the number itself, and take some time to actually write this out. Okay, don't do all of this in your head. I don't want you to make mistakes right now. Write this out because we're just learning it. Okay, don't take shortcuts now. So since we have a cube root, we're looking for perfect cube numbers. I want you to all think of a number, perfect cube, look at 24, that divides 24. What is it? What is it? It's got to be a perfect cube. It's got to be a perfect cube. A number that you can think of that says, I can take a cube root of that number. So while we can do 12 and 2, can you take a cube root of 12?
No.
Cube root of 2? No. So don't pick those numbers. Pick different numbers. What number can you take a cube root of that divides 24?
8.
So pick 8. 8 times 3, actually, gives you 24. Why did I pick 8? I take the cube root of 8. That's why I picked 8. The one do 6 and 4 can't take the cube root of those numbers. Are you starting to see what number, why I'm picking the numbers I'm picking? So now, a to the 9th, we now work on our variables. A to the 9th, we're going to write this as many powers of a to the, what power? Are we looking for squares? Should I write a squared times a squared times a squared times a squared? Should I do that? Why cubes? Yeah, sure, cube roots, okay. So I want, tell me how many I need. A to the, times what? Times? Anything else? Is this still a to the 9th? Why would we pick the third powers again? Because everywhere we have a to the third power, we're going to be able to cross it out, take an a outside of a radical. How about b to the 4th? B to the 4th. What do I want to write that as? You have choices, right? You can do b squared times b squared. Is that a good choice for you here? No, we want what? Cool. Now, everywhere we match the power with the root, we crossed out. Everywhere that we don't, that stays inside of a radical. Here's the reason why, again, I'll show you this step one more time. Cool. Now, everywhere we match the power with the root, we crossed out. Everywhere that we don't, that stays inside of a radical. Here's the reason why, again, I'll show you this step one more time. This gets annoying though, so ultimately we're going to skip this step, because this kind of sucks. I don't want to have to write this every single time, because you'd write the cube root of 8 times the cube root of 3 times the cube root of a cubed times the cube root of a cubed. Okay, threes. Cube root of a cubed times the cube root of b to the 3rd times the cube root of b. It works because you can do this, because you can split that up. Do you see where these numbers are coming from, first of all? I'm just splitting this up. 1, 2, 3, 4, 5, 6, 7. Okay, 7, I got it. So we're just splitting that up. But everywhere you see, you can simplify this one, and this one, this one, this one, this one, but not these two. Do you guys see what I'm talking about here? So while we could do a 2 here, you can't do anything with this one. While you can do an a here, and an a here, and an a here. That looks like a 9. And a b here, you can't do anything with this one. Nudge your head if you're okay on that step. This row, you guys all right with that?
What are you going to do again? 3.
Cube root of 8 is 2. So now you'd have to simplify all this stuff. Put the roots back under one root. Put your variables that are being multiplied together as powers. So we'll have a 2. We'll have an a to the 3rd. We'll have a b. Can you tell me what goes inside of my cube root?
3D.
Got the 3 still, got the b still.
That's your
That's as good as we can make it. You can't simplify 3. Please don't do this. Please don't go, oh, cube root of 3, that's a 1. Okay, we don't do that. But the only numbers you can take a cube root of are 1, 8, 27, and 64, and then 125. That's it. That's it. How many people feel okay getting from, I'm going to have you raise your hand here, getting from here to here, raise your hand. Okay, that's probably the most important step, from here to here, actually knowing what to split up. How many people feel okay getting from here to here? And then, motions, okay? Extra 7. Squares. Shouldn't be looking for perfect cubes. Should be looking for perfect fourth powers. Perfect fourth powers. Okay. So the first thing we do is 32. Just think in your head, think of a number that you can take a fourth root of that divides 32. Now, if you have a hard time dealing with this, start taking the integers and multiplying them by themselves 4 times. Those give you the numbers you can take fourth root of. So for instance, the first one is, don't start with 1. 1 times itself is just going to get 1, okay? Start with 2. 2 times 2 times 2 times 2 gives you how much?
16.
Does 16 go into that number?
Yes.
Just take it. 3 times 3 times 3 times 3 is already 81. That's way too big. Okay, so when we're looking at numbers to the fourth power, 2 and 3, that already gives you 16 and 81. 16 goes into this stuff. So I'm going to write this as the fourth root of 16 times what for 32, ladies and gentlemen?
2.
Okay, and then, oh, x to the 7th. I need to be really good at breaking up x to the 7th. X to the 7th, I should write this as what times what?
You said 4 times x.
Good, we want the fourth because that's, we know we can split that up. We can take the fourth root of x to the fourth and get x. So I don't want x squared, so I don't want x to the thirds. I'm going to get an x to the third by coincidence, but I'm not looking for that one. Do you understand why I'm taking x to the fourth power here, folks?
Yep.
Okay. Now, I'm going to omit this step. I'm going to go directly to the next one. So let's see, I want to show you how that's done here, all right? Firstly, you're going to cross out the things, the items, the factors that you can simplify. So for instance, the fourth root of 16, how much is the fourth root of 16?
2.
So we're going to cross this out, and we're going to put a 2. Because 4 root of 16 is 2. It's just like splitting this up. We're just doing that, okay. What's the fourth root of 2? Can you do that?
No.
You're going to circle it. Whatever you circle stays inside your bracket. What's the fourth root of x to the fourth? Yeah, the power matches the root. That's why we picked it. That's why we did that. Cross it out, put your x. What's the fourth root of x to the third? Can you simplify it? Do you notice how the power is less than the root? It stays. Circle it. Once you've circled, you write it back inside your root. Everything else you've already taken care of. So we still have a root of 2x cubed. Now I made a very common mistake here on purpose to show you something. What mistake have I made? I made a mistake.
You crossed out the other half.
I didn't mistakenly cross out anything. I crossed out everything perfect.
You back 4.
Okay, this happens all the time. People will get this perfect, they'll get this perfect, and they'll make a mistake, and I have to mark out 2 points for this mistake. What mistake was it?
That's below 4.
Yeah, that you just changed this from a fourth root to a square root. Is that good? No, you won't do that. Square root, you'd still be able to simplify that, wouldn't you? This is a fourth root though. Now you're done. Okay, so don't lose the type of root that you have. Try 2 of these examples on your own. Then I'll show you how to work with some quotients, and we'll be done. we're going to start on the first one up here. Square root of 36z to the 7th. First thing I need to do is write this as many perfect squares as I can. 36 is already a perfect square. That's nice. So 36. However, z to the 7th, I'm going to write this as z squared, another z squared, and z. This is what some of you feel like doing in my class, right? Get it? As a joke. Very funny. So when we do our square roots of 36 and z squared and such on, we get a 6, a z, a z, a z, but this one stays inside of our square root. So our final answer here is 6z to the 3rd square root of z. I need to know how many people got it. Good for you, okay? That's good. You see why this works. Z to the 7th, z squared, z squared, z squared, z. That adds up to z to the 7th. You're matching up the power with the root. So square roots and square numbers. Next up, cube root. Cube root of 32, x to the 4th, y to the 7th. Now we can't take a cube root of 32. That's not a perfect cube number. But we are going to think of a number that you can take a cube root of that goes into 32. Did you find that number? I hope so. Did you? How many people found it? Well, that's about half of you. Oh, that's more than half of you. Okay, you're just lazy and raising your hand. I see. Wow. So 32, we're going to write this as, instead of 32, some perfect cube, that's 8, times whatever else it takes, that's 4. You need to write that as 8 times 4. The reason why, you take the cube root of 8. You can't take the cube root of 4, it's going to stay inside of a radical, but you can't take the cube root of 8. Now, x to the 4th. Can you please tell me how I'm going to write x to the 4th power, please? Good, okay. As many x cubes as I can, because I know power root, that's what we want, times whatever else it takes to match up to x to the 4th, or to add up, because we're adding exponents. Now, y to the 7th, same idea. Y to the 3rd, y to the 3rd, y. This is still y to the 7th. I'm just taking as many y to the 3rd powers out of that as I can. Did you make it that far? Okay, now we can cross stuff out. That's the best part. We can simplify. The cube root of 8, that gives you 2. Cube root of 4, can I cross that out? That stays. Cube root of x cubed, great, that's x. Cube root of x, can I cross that out? That stays. Cube root of y cubed, y. Cube root of y cubed, y. Cube root of y, no. Only the y cubes, because those match up. So whatever I circle stays inside of my radical. I'm going to simplify this stuff. 2xy squared, cube root of 4y. That is as far as we can make it. Don't forget about your cube root of the inside stuff. What did I do? Oh, I forgot the inside stuff. Ironic. Cube root of 4y. That is as far as we can make it. Don't forget about your cube root of the inside stuff. What did I do? Oh, I forgot the inside stuff. Ironic. You know what happened? These glasses have that thing right there. I couldn't see it. It's just like that. I saw the 4. That's weird. Darn eyes, not seeing stuff. Never. Now, we're probably not going to be able to make it through all 3 of these in the last minute and 48 seconds, but we're going to try at least a couple. Here's the biggest point I can make about this. Before you do these problems. You absolutely have to use the quotient rule to combine them. First two, you could do them without it, but it's gonna be very hard to do this last one unless you do what I'm telling you right now. You have to combine those roots first before you simplify. Write that down. Right? Combine roots first before you simplify. Combine first. Why? It makes things easier. Oh my gosh. If you do this, look at this. I want you to look at this problem for me before we're going to do a couple of those. But on this problem, if you try to, you can simplify that, sure. You can simplify this one. That negative's going to probably throw you for a loop. You're like, what the heck? But then you're going to have to combine them anyway and simplify again. That's going to suck. So instead of simplifying, then combining, then simplifying, that's 4 steps. You can do this in 2 steps. You combine, then you simplify all at once. Isn't that better? That's better. Combine them first. Here's what I'm talking about. You're going to see this. I could simplify that. That's going to be 5 root 3. The root 3's would cross out. However, if I consider the quotient rule says this is the same thing, powers match up, as 75 over 3. True. I can take 2 roots that are being divided, make them 1 root inside of a radical. What is 75 divided by 3?
25.
Can you take the square root of 25?
5.
That's way easier than simplifying here, doing that whole process, and then ultimately finding the square root. What is 75 divided by 3?
25.
Can you take the square root of 25?
5.
That's way easier than simplifying here, doing that whole process, and then ultimately finding the square root. Are you with me on that? Okay. Last thing I got to show you today, we're going to do this problem and we'll be done. What to do with that 3? Is this 3 on the numerator or denominator of our problem here? It's going to stay on the denominator. This 3, it's not inside of a root. Here's what this means. This means 1/3 times the square root of 80y over the square root of 5. That's what that means. Notice how the 3 would be on the denominator of that problem. Not if you're okay with that. Yes, no? So what you're going to do, leave that 1/3 out front. Don't even worry about it until the end of your problem. You can't forget about it, but don't even worry about it. Break that 3 off. It's not part of your root. It's just being multiplied 1/3 times this. Denominator, denominator, denominator. Then combine your roots. So you'll have 1/3 times the square root. Since they're square root over square root, I can do 80y over 5. What is 80 divided by 5? How much is it? Is it? So instead of 80y over 5, you're just going to put 16y. That's nice, right? 80 divided by 5 is 16. So we have that. Can you take the square root of 16? Can you take the square root of y? Are you going to be able to simplify that? That's power 1, that's a root 2. So the only thing we'd be able to do is do 1/3 times the square root of 16, remember you multiply here, is 4. I can't simplify the square root of y. Get that. How many feel okay with this so far? What you can do with 1/3 times 4? 1/3 times 4 is like 1/3 times 4 over 1. You get 4/3 square root of y. Or 4 root y over 3. You just put that 3 right back on the bottom. That's an appropriate answer. You're completely done with that. This made sense to you today. Good, all right. We'll work on a couple more of these next time. We'll do 2 next time, and then we'll do 1 on your own and be good. So last time we were still talking about these radical expressions, and what we realized is that in order to combine or simplify these radical expressions, the first thing you have to do is combine them. I told you that really what we really never want to do. We never want to simplify the numerator, simplify the denominator, and then combine them because you're going to have to re-simplify it all over again. So I think last time, the last couple examples were combine those radicals first using the quotient rule, and then simplify them. Do you guys remember that from yesterday? So when we look at this problem, firstly, can you combine them? Yeah, what tells you you can combine them?
The cube root.
Good, they're both cube roots. I mean, the quotient rule said if you have the same type of root, you can put them under the same fraction, under the same radical. Have one fraction under that radical. Do you remember that? Okay. Also, that 5, is that 5 inside the cube root? That 5, what it means, just like the 3 did on one of our previous examples, this means 5 times something. So what we're going to do with our problem here, before we even start it, we're going to take this 5, since it is being multiplied here, we're just going to kind of pull it out. To the side and hold it there to the end of our problem. Now, is the 5 on the numerator or the denominator? What that means is that this is going to be on the numerator for the whole entire problem. Are you with me on that? So it's not going to move to a denominator or anything. The 3 last time on the example, you remember from yesterday? 5 times this radical expression. Now, what tells you that you can combine those radicals is that you have the same exact type of root on both the numerator and denominator. If you ever have that, if you ever see this, and you're talking about simplifying radicals, the first thing you need to do, make one radical out of it. Please, please do not simplify this one first and try to simplify this. You can't even simplify that one. Did you guys see that? Power is less than the root. That 3 is not a perfect cube. You can't even simplify that. So at some point you would have to combine them anyway. Do it first, that way you don't waste your time. Up here, you simplify this, then you combine them, then you have to simplify anyway. That would be a tremendous waste of time. And it's hard to do that when I throw negative exponents at you too, which I'm going to do in just a little bit. Okay, so very first thing we're going to do, do it first, that way you don't waste your time. Up here, you simplify this, then you combine them, then you have to simplify anyway. That would be a tremendous waste of time. And it's hard to do that when I throw negative exponents at you too, which I'm going to do in just a little bit. Okay, so very first thing we're going to do, we're going to leave this 5 alone 5 times, and we're going to make this one radical. We're still going to have a cube root, that doesn't change, but inside of our cube root, we're going to have 162 x to the 8th over 3x squared. Not sure if you're okay with that one. Just a little step, right? Just a little step. Make that one root first. Why?
Now you can simplify.
You can, right? Can you simplify 162 over 3?
Yep.
Do it on a calculator if you haven't already. How much is 162 over 3? How much? 54, okay. Can you simplify x to the 8th over x squared? Sure, hey, exponent rules. That's why we covered this. So if you're looking at this problem, well, I know this 5, I'm leaving it out there. But under my cube root now, without doing any radical simplification, we're able to make this fraction a whole lot better. I know that 162 over 3 is, you guys said 54. Can you tell me how much is x to the 8th over x squared? What do you do with those exponents? And so we're going to get x to the, perfect. Remember that? Subtract exponents. Now I want you to look at this thing. Can you simplify that?
Yep.
Is it easier to simplify than this? It's even easier. That's even better. This is what we want to deal with. So I'm going to make a real strong point here. You must combine before you simplify. I'm going to give you a problem very much like this on the test. The people who simplify first probably aren't going to get it right. The people who combine them first, you're definitely going to get it right. Combine it first, then simplify, no big deal. The one I'm going to give you on your test is actually going to have some negative exponents on there. And so you're going to have to know how to deal with that. So make sure you're combining first before you're simplifying. Let's go ahead and finish this off the rest of the way. I'm going to leave that 5 out there still. It's just going to be hanging out 5 times. And then the cube root of 54x to the 6th, I haven't lost my cube root the whole way through. You can't lose your cube root. We're going to look for 54. Can you think of a perfect cube that divides 54?
27.
What was that? 4 is not a perfect cube. 27, sure, that's a perfect cube. So we're looking for this perfect cube. So remember, on this case, we're not looking for numbers like 9. We're not looking for numbers like 16 or 4. We're looking for perfect cube numbers, which would be 8 or 27 or 64. Now there's only 2 that we have a choice of because 64 is already too big. The only ones you can choose from are 8 and 27. So you need to know what type of root we're dealing with. If it's a cube root, we're looking for perfect cubes. 8's not going to work. 8 doesn't go into 54, but 27 does. Remember 27 as a perfect cube? We just cube root of that. So 54, I'm going to write the 27 first, times, what is that, 2? And the x to the 6th. I can deal with x to the 6th. How am I going to split up x to the 6th in this particular case?
Times x squared with their power.
I could do that, or, yeah. We break off as many x cubes as we can. Why are we choosing x cubed in this case? Yeah, we know that everywhere we see a power 3 with a cube root, we're going to be able to cross it out and take x out of our radical. Let's go ahead and do that. I want you to notice that I haven't lost the 5. The 5's still up out here. I haven't done anything with it. That's okay. I've not done a thing with it. You just can't lose it. Don't lose your 5. And don't lose that little 3. Don't lose your index. So we've got the 5 still hanging out. At this point, though, we're going to simplify the rest of our problem. Notice the 5 is right here. What's the cube root of 27? Cross out, put a... What's the cube root of 2?
2, 300.
Okay, so what am I going to do with that?
So we're gonna do the cube root.
I circle it, signifying I'm going to leave that in my cube root. Cube root of x cubed gives me how much? Cross it out, that's x goes outside of a radical. This one, oops, I did the wrong thing. This one also gets crossed out, that gives you an x. Whatever's left circled stays inside of the cube root. Raise your hand if you're okay with this so far. Middle row, are you okay with this? Okay. Can I make this any prettier, any better looking?
Yeah, just combine the outside.
That's 5 times, right? 5 times 3. I can make that into,
15x squared.
good, yeah, that's going to be x squared. I certainly don't want to forget this cube root. And there's only a 2 inside. So our answer is 15x squared cube root of 2. Feel okay with this so far? Told you this was fun, huh? Lots of fun. What would you rather be doing on Thursday, honestly? I mean, nothing, really. Nothing. Not sleeping. You'd rather be dealing with negative exponents, clearly. Clearly.
Friday.
Oh, negative exponents only happens on Friday.
Yes.
I see. Oh my. Oh my. What's different about this problem than the last one? Okay, fourth root, that's one. And then the other one? Yeah, you got negative exponent. Hey, let me tell you something. If you forget what I tell you and you forget to combine these first and you try to simplify the top and simplify the bottom, because that's all I'm going to put on your paper is simplify. And you're going to have to know what to do. So if I put simplify here and you start simplifying this one without combining these first, you're not going to make it. You're not going to make it. Unless you realize you have to combine them at some point anyway, but it's going to get pretty confusing if you do that. Because you're going to have a lot of stuff going on up here, and then you're going to try to combine that with the stuff down here, the negative exponents, which you cannot simplify this in any way right now at all. You're going to be very confused on what to do. The goal of this is to simplify. However, whenever you have the same root over the same root and you were trying to simplify, put them together first. You know why? If you look at the last example, what happened here was whenever we had the common base, we were able to combine them, right? And change two problems into just one problem, which was a little bit easier even. That's the whole idea. So instead of dealing with x to the ninth and x to the negative 3, that's a common base. We are going to be able to combine them. Do you guys see it? You're going to be able to combine them somehow. And that's going to be easier to deal with. So that's the whole purpose here in combining your radicals. So whenever you see the same root over the same root, you got to combine them. Now also, we've got a 3 up here just like we had the 5. That 3, I'm going to leave it hanging out just like I did the 5 over here. Now, is the 3 on the numerator or denominator? Notice how the 5, we left that, it was on the numerator, right? This wasn't 1 over 5, this was 5 over 1 the whole way through. If the 5 had been on the bottom of my fraction, this would be 1/5, and I would be getting this whole thing over 5. Are you with me on that? That would be a 3, and this would be over 5. Let's do the same thing here. So I'm going to start off the same exact way and have a 3 times 4th root of all this junk. Okay, that's the first step. I gave you the first one. Now, can you please tell me the next step? What would I do now? Combine them. Great. What lets you know that you can combine these?
Yeah, the same root sort.
Okay. Same type of root, yeah. If that was a 4th root and that was a 3rd root, you couldn't do anything with it. But fortunately, they're the same root. So we're going to make this, it's going to look identical. The only difference is this thing is not going to be here. You have one big 4th root. So the 3 is going to stick out front still. Make one big 4th root out of it. One big 4th root. Okay, so on the right-hand side of the room, what do I do now? What now?
It should be 32x to the 12, y to the 5.
So we're going to combine them, sure. And we know exponent rule, so this should not be the big deal here. The big deal is actually the simplification part. I've already taught you how to do this. I've already taught you how to combine these things as well, right? I've already taught you that. That's old stuff. Okay, so we look at the number first. Of course, there's no constant term over here. So we're going to have just the 32. Now, I am going to deal with these problems individually. I have the x's, I have the y's. So I'm going to do those piece by piece. Let's please look at the x's first. We've got x to the 9th over x to the negative 3. Now, you tell me, what do you do when you have common bases being divided? Do you add exponents or subtract exponents?
Subtract, that's a negative
Subtract.
6 them.
So when we do it, we do have x to the 9th, and we are going to subtract. But be very careful. What are you subtracting? Are you subtracting 3? No, because this right here. That will be subtracting 3. That way you get x to the 6th. You with me?
Yes.
We're actually subtracting negative 3. Now I'm going to draw it a little bigger so you can see it better. This would be subtracting 3. Right now, we're not doing that. We're actually subtracting negative 3. That's like adding 3. So when you are dividing by a negative exponent, you actually add that up there. And you can pretty much see this if you really want to think about it this way. If that's a negative exponent, this means it's in the wrong position. It means it actually belongs up here on this fraction. That would change it to x to the 3rd, positive 3. Does that make sense to you? Then when you combine them, you would see you would get x to the 12th. And that's exactly what we're going to get here is x to the 12th. Does that reasoning make sense to you? Okay, so we're not going to get x to the 6th. You're subtracting a negative. That's x to the 12th. Because of that reason. How about the y? Are we going to get y to the 6th still, or y to the what? Okay, that has a little power 1, even though we don't show it. It's got a power 1, so we do the 6 minus 1, that gives you y to the 5th. Now what do you do?
Now you got to break apart 32, so you can get a 4th root.
Okay. And we got to do, can we simplify these? What do you think? Well, let you know you can simplify these.
They're greater than 4.
Okay, so the power's bigger than that root, we can do that. Do it. Go for it. See if you can simplify the first one. If you finish quickly on that simplification, try this next problem. That's what we'll start with after this. Okay, so we're looking at this one. I'm going to finish this thing off. I'll give you some more time to do this in just a second. Let's go ahead and work on this so you know whether we got it right or wrong. Firstly, with the 3, we're not going to do anything with that 3. We're just going to leave that out front for now. But we are going to try to simplify the inside of our radical right here. Now that 32, we're looking for a perfect fourth power that divides 32. The only perfect fourth power I know that's less than 32 is actually 16. That's 2 times 2 times 2 times 2. That's only 1. So unless that goes into it, we're not going to be able to simplify this. 16 fortunately does go into 32. How many times? So 16 is the perfect fourth power we were looking for. 16 times 2 gives us 32, so we're going to be able to split up our 32 like that. Now, x to the 12. I'm going to look for as many x's to the power 4 as I can. In this case, we have x to the 4th, and we're going to have that 3 times. I'll make sure that I double check to see that that actually adds up, because we're adding those exponents now, since we're multiplying to 12. It does. 4, 4, 4, that gives us actually 12. So we know we have the same expression so far. Now, the y to the 5th, I can also break that up. The power is greater than the root. That means I can write this as, I'm going to choose to do y to the 4th times y. Like as many y to the 4th as I can, and whatever is left over, that still makes up y to the 5th. Did you write it like that as well? Good deal. Now, we're still going to leave that 3 out there. That 3 hangs out until the very end, until we can multiply it by something. We'll take the 4th root of 16, that gives you 2. 4th root of 2, I can't do anything with that. I'm going to circle it, it's going to stay inside of my radical. 4th root of x to the 4th, that gives you x. Then x, then x. Another y, but that y I can't do much with. The power's less than the root, that means I can't simplify it anymore. So there's only 2 things left in my radical. Definitely want to make sure I have a 4th root. Make sure that 4 is there. Then I'm going to have a 2y inside of it. I'll clean this up a little bit. I know 3 times 2 is 6. That's why we left the 3 out there. We can lose that. This gives you the x to the 3rd, y, and then we want to make sure we do a 4th root of 2y as well. That's as simple as I can make it. That's a lot more concise than this. Looks a lot better than that, doesn't it? That would be much easier to work with than this and another problem. How many people were able to make it down that far? Good for you. That's good. Okay. Now, I want you to continue working on this one. Notice a couple things about this. Firstly, we have the same type of root or the same type of root. You are going to combine those first. The 5, however, is not on the numerator like the 3 was. It's on the denominator. So keep that on the denominator. If you end up multiplying by 5, if you end up multiplying by 5 at the end, and I did something wrong. Right here, the 5 should be on a denominator at the end of your problem. If you do it the same way as this problem, you've done something wrong. Okay? Because right now, this 3 was on top. That's why we multiplied by 3. This 5 is on the bottom. We should have 1 over 5 somewhere. So continue working on that. I'll give you about another minute. Now, while it's outside the radical, we are going to have to deal with it at some point. We don't deal with it initially, but we do need to notice it is on the denominator of fraction. So when you're going through this problem, sure, take the 5 out. But we can't write it as 5 times something. That's not right. That would move it to the numerator of a fraction. That'd be like 5 over 1. When in fact, what we really have is this is like 1/5 times. That 5 is on the denominator, the 5 is on the denominator. So instead of 5 times, you're going to have 1/5 times. Did you guys do that as well? Yeah. So make sure you have that in the appropriate spot. Now the rest of it, that's okay. We're going to break that off, and we're going to combine these radicals. Since I have a cube root and a cube root, I know I can write one large cube root of this fraction as being part of the radicand. We certainly don't want to try to simplify it first. That's way too hard. Make sure we combine them, especially with that negative exponent. Make sure you combine them. That takes care of the negative exponent. There's nothing you can do with it here, but here you can combine those and that negative exponent's gone. Does that make sense for you? That's kind of nice. So we'll leave that 1/5 up front. Again, we're not going to touch it yet. And the cube root will be able to simplify. So 40 over 5, that's going to give you 8. X to the 5th over x to the negative 1. You're subtracting exponents. 5 minus negative 1 doesn't give you 4. Gives you, good. So you're taking 5 minus negative 1. 5 minus negative, that's adding. Lastly, we got y to the, now that you do still subtract. You subtract in both cases, but we have 7 minus positive 2. That's going to give you, that's what it did. Show of hands how many people were able to make it that far. Good, that's the most important step right there. You can make it that far, you have a much better chance of succeeding in this problem right now, because this is something we've done before. At this point, we'll try to break this up to simplify this. It's a cube root, so we're looking for perfect cubes. Of course, 8 is already a perfect cube, so I'm going to leave that alone for now. I know the cube root of 8 is 2, so why change that? We don't want to do that. Inside, though, I have x to the 6th. I'm going to write as many x to the 3rd powers as I can. Fortunately for us, that still is x to the 6th. We have 2x cubes. We're not going to have any x's left inside a radical. Y to the 5th, I know I want to break off a y to the 3rd, because that's going to simplify, and I'm left with a y to the 2nd. Still so far so good? All right, cool. That's the fun part. Get to cross some stuff out. We're still going to leave that 1/5. Cube root of 8 gives you 2. Cube root of x cubed gives you x. Cube root of x cubed gives you x. That's why we did that, because every time the power matches the root, we get to cross it out, take an x outside, or a y outside in this case. And lastly, well, the y squared, the power is less than the root. It's certainly not the same thing, so we can't cross it out. We can't take the y out. We leave it inside of a radical, so we get a cube root of y squared. Did you make it that far? Yeah, no? Good, all right. The last thing you got to do is clean this thing up a little bit. Now, when you do that, I know this is going to be 2x squared y and a cube root of y squared. What do you do with the 5, though? Yeah, it's just going to be on the denominator. 1/5 times any expression says you're going to have that expression over 5. Multiplying by a fraction is the same thing as dividing by its reciprocal. So if I multiply by 1/5, the same thing as dividing by 5. So this is the same thing as that. That's a true statement. So if you have the 5 on the denominator, notice 5 was on the denominator the whole entire time. Just stuck on the denominator. We actually didn't even do anything with it. Now, if this had been like 10 or 15 or 20 or something, you could simplify that for sure. But at this point, we can't simplify that any more than we just did. Did it make sense that the 5 stuck on the denominator the whole time? Definitely don't want to have 10 right here. You give me 10 right there, that means you multiply by 5 instead of multiplying by 1 over 5. That's a different expression. Which brings you to feel okay with what we just talked about. Might want to try some of those problems. There's several of these on the homework. Make sure you get them right, check your answers in the back of the book. Make sure you can do them without following your notes all the time, okay? You need to be able to look at that and be like, oh yeah, I know exactly what to do. Bam, bam, bam. When we get time for the test, that's how well you need to know it. Now, are you ready to move on and start adding and subtracting these things? Oh yeah. I'm excited. I'm excited about it. I don't know you guys. I think I saw some head shakes. No, I'm not ready. I'm not ready. Come on. No, you're ready. You're ready. Trust me, I'm the teacher. I know. I can see it in your eyes. You guys are just, you're sandbagging, right? No? What? Sandbagging? You ever heard the expression sandbagging? No. No, am I that old? How many people know what sandbagging means? Okay, you're younger than me, that's good. Sandbagging means that you pretend like you can't get something, that way when it comes time to actually do it, you either don't have to do it or you perform really well at it. So it looks like you're not. So it looks like you just, like we used to sandbag it at weightlifting class all the time. So like when you started out, you're like, oh, this is really hard. And then when it came time for you to actually do it, you just go, and that way you would get full credit for the class because you sandbagged, right? So you didn't actually perform well, you didn't actually improve. You just looked like you improved at sandbagging. Anyway, you learned something about sandbagging today. That was all about math, wasn't it? So section 10.4, we're going to add and subtract some radicals. Now here's what you need to know about adding and subtracting. This is going to be very, very, very similar to doing things like this. Can you add those together? How much you get? Wait, 12 what? 12x. Oh, but that's the whole question I have for you. Do you get 12x or do you get 12x squared?
12x, you're not multiplying.
You're not multiplying, that's right. You have 5x's here, you have 7x's there, together you have 12x's. You don't have 12x squared, right? When you go to the grocery store and you get 5 apples, and you go, I need more apples. So of course, it needs more apples. And you get 7 apples, do you get 12 square apples? That'd be kind of cool, but no, that'd be easier to cut. Needs more apples. And you get 7 apples, do you get 12 square apples? That'd be kind of cool, but no, that'd be easier to cut. But you don't, right? You still have 12 apples. You don't change the units just because you're adding things together. If you have it's $5 plus $7, you don't get $12 squared, right? That doesn't make sense. So when we're adding, when you're combining like terms, you look at these coefficients. Because you're able to add these, you are able to add these because you have an x, you have an x. If this was an x and that was a y, could you add them?
No.
If this was an x and that was an x squared, could you add them?
No.
Okay, if you keep that in mind, adding and subtracting radicals are going to go very smoothly for you. Because what we're doing, adding and subtracting radicals is very similar to combining like terms. terms to combine there? Okay. Combine these. Here's the same type of root. Those two things. Let's look at this one. Remember, we're looking for two things here. We need the same root. Let's look at this one. Remember, we're looking for two things here. We need the same root. Same radicand. Do you remember what that word radicand meant? I've been using it a lot up here. I had you go over it a little while ago. Radicand was
So number outside.
whatever's inside there is called your radicand. That's right. So when we look at this, it is like combining terms. Instead of looking for a variable to a power, you're looking for the same root, same radicand. Do I have the same type of root here?
Yes.
Yeah, what I mean there is that's a square root, that's a square root, that's the same root. This, folks, is identical to looking at the exponent here. That's what you're doing. A root is an exponent. You really are looking at the exponent. You're just in a root form. This would be 15 to the 1/2 power. This would be 15 to the 1/2 power. Are you with me? That's what that is. So you are looking at the exponent when you talk about the same root. Now the same radicand, that's like having an x and an x to some power, or an x and an x. So we look at the same root because that's our exponent, same radicand because that's like our base here. So do we have the same root and the same radicand? Yeah. Are we going to be able to add these things? Now the question is, what do you get when you add this? I know I'm probably going to get like a 7, right? Probably going to get a 7. Just like here, I had a 5, I had a 7, gave me 12, I get a 5, and a 2, that's giving me 7. The question is, what do I get out of the root 15 and the root 15? Well, we're going to go ahead and look back up here. When we added a 5x and 7x, did the x change at all? No, we didn't change it. We didn't get x to the second, right? So we're not going to get like a 4th root. We're going to still have a square root. Also, it is still like this. You have 5 x's here, you have 7 x's here, together you have 12 x's. You have 5 root 15s, you have 2 root 15s, altogether you have 7 whats? It doesn't magically change to 30. It does not magically change to 30. That's a big mistake that people make. People think addition, in their heads they go, hey, it's kind of fun, 7 root 30. Woo! No, we can't do that. Okay? You're adding like you're doing like terms. You have 5 of one thing, you have 7 of one thing, you have 12 of that same thing. You have 5 of this thing, you have 2 of this thing, you have 7. Did I say 5 and 7, you get 7 still? Oops. You get 12. You have 5 of this thing, you have 2 of this thing, you get 7 of that same thing. That'd be the 15. You don't change the root, and you don't change the radicand when you're adding. Okay, 9 cube root 2y minus 13 cube root 2y. The first thing you must check for if you're trying to combine these radicals is like combining like terms. What are you looking for in this case? Okay, do we have the same root? That's like your exponent. That is your exponent. And we also have to look for the same. Do we have the same radicand? Can I combine these things? The way we do that is just like combining like terms, you look at the coefficients. Here the coefficient's 9, here the coefficient, remember you include your sign here is negative 13. So we just look at 9 minus 13. If you can do that, you can do this. How much is that? So we get negative 4. What's the rest of it? Still a cube root, okay. Of what? Perfect, that's it, that's it. It's kind of easier than you might have thought, right? I mean, really, as long as you have the same thing, you're not changing that. You're just adding or subtracting coefficients, just like you did with like terms. This is combining like terms, only now your terms are not x's or y's, they're roots. That's it. Okay, let's go ahead and combine this one. How much are we going to get out of that one?
Can't combine.
Wait, why not?
Because the radicand's different.
Well, wait, I still have a 10 and a 10, and there's a root around that. You mean I can't do that still?
The radicand, one's cubed and one's squared.
Oh, I see. So this would be like having a different power. It'd be like trying to add these together. While the x's were the same, the powers were different, and you cannot combine those. We weren't able to combine these, we can't combine those, right? It's a different power. This is like having a different power. So in this case, what would you do? You leave it. That's what you're doing. Okay, let's look at that one. Do I have the same type of root?
Yes.
So we've eliminated the problem we had here. Do we have the same radicand?
No.
Okay, so am I going to be able to add those?
No.
No, I'm not. No, I'm not. Not right now. However, I want you to look at that very carefully. I want you to look at the square root of 50 and the square root of 18 because that's what we have, right? Can you simplify those?
Yes.
I sure hope so because we just finished that section. If you can't, well, I did not do my job right. We should be able to simplify those things. So what I'm trying to tell you here is that if you can't initially add them together, here if you look, that was simplified, that was simplified, that was simplified, that was simplified, and these were both simplified, as much as you could do. And that's why we could easily tell whether we could add them or not. Right? However, in this case, well, that one, I mean, the roots were different. There's no way you can add those. But in this case, we have the square root of 50. I know that 25 goes in that number. That's the square root of 18. I know that 9 goes in that number. We're looking for perfect squares. So I'm certainly going to be able to simplify those things. So before you say yes or no, whether you can add those or not, you better simplify them to make sure they're in the simplest form. That's why we spend all this time. If we hadn't done simplification, you look at that and go, no, I can't add those. When in fact, if we simplify them, we might be able to. So let's spend some time right now and simplify your radicals first. Let's simplify our radicals first. Square root of 50, as we already talked about, we're looking for perfect squares. I know 25 divides that number. I'm picking 25 because I'm not going to really spend a whole lot of time on this. We just did that section. 25 because I can take a square root of that, and we're looking for perfect squares here. Plus, that 5 hangs out the front. The 5 hangs out there. Square root of 18, I know that's going to be what two numbers?
2 and 9.
Good. I'm going to write the 9 first because that's the number I'm going on. After that, we simplify it's like 2 problems in one. Square root of 25, ladies and gentlemen. And how about 2? What's going to happen with that? So would you agree that out of this part, I get 5 root 2? Okay. Then add a plus. Hey, don't lose that 5. That means 5 times whatever you're going to get. This means 5 times whatever you're going to get over here. Are you with me on that? What's the square root of 9? So we're going to have 5 times 3. Ultimately, that's what's going to happen. And then the square root of 2, I can't do anything with that, so I'm going to get the root 2. I'd like to see if you're okay on that. Raise your hand if you are. All right with that. Good, all right. Basically, just simplifying this one, simplifying this one. That gives that. Let's make this a little bit prettier before we try to combine these things. I know the 5 root 2 up here, that's as good as I can get. But here I have 5 times 3 root 2. How much does that give you? 15. Sure. 50. Does it change the root 2? This is not a distribution problem. This is all being multiplied together. So when you had 5 times 3x, you just put 15x, right? You're not going to do 15 root 10. That's not what we're doing. This is not distribution. This is just multiplication. You just multiply those numbers. If you think about this like terms, if you think about your root like a variable, it's not a variable. Okay? But if you think about it like it's being treated like these numbers, it's a good stepping stone for you. It's similar. Not exactly the same, but very similar. Hey, can you combine those? Yeah. Those are the same. I've got the same exact root. I have the same exact radicand. I've got 5 here. I've got 15 here. Total I have how much? Square root of 2, yes? You sure? Yeah, that's exactly right. So we're simplifying those radicals first. A lot of times we're going to get the situation where we have similar, or the exact same root, same radicand, we can add them together. Ready to go on? Sure? Questions on that one? All right. Not ready to go on? All ready? Question? You okay with it? All right. She's saying thanks. She's shaking her head. I'm ready. She just doesn't want to go on. She wants to waste the last 5 minutes playing. All right. Shoot, we got 7 minutes left. While y'all come in 2 minutes late, let's spend 2 minutes extra. You're going to get your 50 minutes worth, I guarantee that. All right, oh my, wow. First, let's see if we are maybe even going to be close to adding these things together. First thing you check for is the root. Okay, that might save you a lot of time. You're going to simplify it regardless, but at least you'll be able to know whether you might be able to add these together or not. Is the root satisfied, at least?
Yes.
Now, we have the cube root everywhere, that's great. Don't lose that 3 when working down. Now, next thing, of course, our radicands are not even close to the same, so we're going to have to simplify these things first. Let's start the easy one. Can you simplify this one?
No.
Please don't ever tell me that's 1, okay? That's the only numbers that we can simplify in a cube are 8 and 27, 64, 125, and so on. So here, I know for sure I'm going to have a plus cube root of 3. Let's work on this cube root of 24 next. Cube root of 24, can you think of a perfect cube that goes into 24?
8.
And remember, we're dealing with cubes, right? The only numbers you can try are 8, 27, 64, and 2 of those are bigger, so only 8 would help us here. I know it's 8 times 3. Minus 4, and then a cube, oh my gosh, 192. But remember, there's only a couple numbers you can even check. You can check 8. You can check 27. You can check 64. Start with the big ones. Start with 64. Does 64 work?
No.
Okay, try 27 then. Does 27 work?
Yeah.
I don't know. I have no idea. Divide it. You get calculators. I don't. 64. Okay, 64 does work. I thought it did. You scared me. What, times 3? All right. So we break that up to 64 times 3. It's kind of nice with cubes, right? Because with you, you can check. If it's not 8, 27, 64, 125, well, you're done. It's kind of nice. So we're going to break that up. We got it. Now we simplify. Just be careful. Don't lose anything here. Don't lose your 4. Don't lose your cube root. What's the cube root of 8, ladies and gentlemen?
2.
So I'm going to have 2 cube root 3. Because there's nothing I can do with that 3. Minus, don't lose the 4. The 4 is going to be there regardless. Cube root of 8, cube root of 64?
4.
What is it, 8 or 4? 4. It is 4. Yeah. I said 8 because I saw that. I don't know why. But yeah, that's definitely 4. It's 4 times 4 times 4 gives you 64. So cube root of 64 is 4. And I have a cube root of 3 still inside of my radical. Plus I've got this cube root of 3. I heard it back in. We're going to clean this up just a little bit, multiply anything that you can before you start combining your roots. So I know 2 cube root of 3, that's good to go. Minus, this gives you how much?
16.
Good. 4 times 4 is 16. Cube root of 3 plus cube root 3. Can we add all of them?
Yep.
We've got the same exact root, same exact radical, so yeah, we can. I don't know what we're going to get. And we can do this 2 at a time if you'd like. We've got 2 minus 16. Wait a minute. How much is this over here?
1.
Don't forget that that's a 1. Okay, this actually counts. There's like a little 1 out front. We don't show it, but this is like having sure negative 14. Plus. Let's try one more today. You're going to get negative how much?
13.
13. Very good. Plus or minus. Let's try one more today, and then we will be done. We'll start this next time. Now we have haven't had any variables yet. Well, except the first one was already kind of done for us, so it's already simplified. But we can still simplify the same way we would before. So if the power is bigger than the root, we can simplify it. If it's not, then we can't, as far as the variable goes. The numbers will do the same exact way. So when we look at this thing, we've got square root, square root, square root. The roots are satisfied. We've got 20x, 60. X, 45x, the radicands aren't. We need to simplify those first. So when we look at the 20x, can you tell me what number I'm looking at for 20, please, quickly? 5 and 4, or 4 and 5. Okay, so 4 times 5x. I'm looking for 4 because it's a perfect square now. Looking for squares. Minus 6 times, okay, the 16. That's already a perfect square. I'm going to leave that to the next step. 16x is great. Plus, how about the 45? What goes into 45? 9 and 5. Great. Squared, 9 times 5x. Raise your hand with me so far on this. Okay, let's simplify. Can you all stick with me here? What's the square root of 4? Do you agree I'm going to get 2 root 5x out of that?
Yes.
Okay. Minus 6. What's the square root of 16?
4.
Watch carefully, please. We're going to have times 4. Then I have, what's inside the square root? X. Good. You okay with that? That's 4 root x?
Yeah.
Lastly, I've got plus. This is going to give you 3 square root of 5x again. Let's do one more step. Multiply what we can. 2 root 5x minus 24 root x. Remember, multiply. Line 24 plus 3 root 5x.
Mine too.
Why can we only combine 2 of these? What's wrong? Okay. While we do have square roots everywhere, this one worked out to be a square root of x. This was a square root of 5x, this was a square root of 5x. So just like we had in the opening of this problem, you can only combine like terms, you can only combine like radicals. So we have a 2 root 5x, we got a 3 root 5x. How many root 5x do I have?
5 root 5x.
5. That takes care of these ones. Then at the back end, I still have a minus 24 root x. Hey, one question, can I combine these and get like negative 19 square root of 4x?
Nope.
No, you can't. You can't do that with like terms, you can't do it with like radicals. This is as much as we do. How many people feel pretty good about what we talked about so far? All right, good. We're talking still about how to add, subtract, and we're going to get to how to multiply some radical expressions. We're dealing with stuff like this. Something like the cube root of 8y to the fifth plus a cube root of 27y to the fifth. Now, ladies and gentlemen, when we're trying to add roots, what do we have to look for in order to determine that we can actually add these things? Okay, you gotta have the same root. Very good. Someone else tell me what else you have to have. Right, radicand, and that's like a base. What we're doing is we're very much like combining like terms because these things technically are like terms. They have an exponent, remember root is exponent, and they have a base, or in our case a radicand. So we really are trying to combine like terms. What do we have to do first, though, before we start trying to combine them? Firstly, are these combinable the way they are?
No.
Well, why not? We have the same root.
Radicands.
Oh, the radicands are different. You must have the same root and the same radicand. We talked about that yesterday. So the first thing we need to do before we start combining that is check to see what?
Simplify.
Let's simplify them. Why don't you go ahead and do that right now? Let's simplify those two roots. We should know exactly how to do that. If you finish that one, quickly, if you simplify that quickly, what we're going to put together, but then we're going to start these two problems too. So if you're already done, maybe start those right now. Root here. We're looking for perfect cubes inside of my root because we have a cube root. Well, first of all, I know that 8 is a perfect cube. That's great. So I don't have to change 8 at all because I know the cube root of 8 is 2. That's fantastic. I don't have to break that number up. So I'm going to leave that as an 8. However, y to the 5th, the power is bigger than the root. And we know that anytime the power is bigger than the root, I can simplify that. How am I going to write y to the 5th so that I can simplify it, folks? Times? Perfect. That's exactly right. Same situation over here. 27 is a perfect cube. I know the cube root of that is 3. That's great. I don't have to change 27. However, the y to the 5th, yeah, I need to write that as y cubed times y squared as well. Did you make it that far, folks? Now's a good part. We get to cross some stuff out. So when we do this simplification, it shouldn't really be the hard part. In fact, this is a combination of two things we know how to do already. We know how to combine like terms. We know how to simplify. We're just doing it now at the same time. Cube root of 8 gives you 2. Cube root of y cubed gives you y. However, the cube root of y squared, the power is now less than the root. I cannot simplify that anymore, so I've got the cube root of y squared. Give me a head nod if you got that one right. Okay, good. Now next up, I still have this plus. Cube root of 27 gives you 3. Cube root of y cubed gives you a y. But then I also have this y squared, so cube root of y squared. Raise your hand if you made it that far. Good deal. Now, can we combine these radicals?
Yeah.
We're looking at two places, actually. We're looking not only at the root and the radicand, but we're also looking at this variable. Those variables, that stands for like terms as well, right? So you gotta have the same exact variable to the same power. So here, basically, everything besides your number has to be identical. Everything besides this 2 and this 3 has to be the same. This 2 and the 3 stands for a coefficient. We know that these right here are perfectly the same. They're like terms. That means we can combine them. So even if you have some variables up front, if they're still the same, you can still add or subtract those things together. You with me on that? Okay, so how much are we going to get out of this? Okay, and the way you'd say that is 5y cube root of y squared. 5y cube root of y squared. So nothing else changes besides that coefficient. Let's go like I want you to try these two on your own. So we're simplifying these roots. Go all the way down, make sure we can add them together if you can. If you can simplify and add them together, do that. I'll be walking around. If you need help on this, raise your hand, let me know. So this is much we're going to be able to simplify this at 25. Minus 3. Well, the 3 is going to stay there. What is that 3 doing next to that root? What's that mean? Okay, so we're going to leave that hanging out till the very end. We just know it's 3 times whatever else we get. Now the 27x, what number goes into 27 that you can take a square root of? Because we have a square root. Good, okay. And lastly, we got 12. Is there a square that goes into 12?
4 times 3.
Okay. Yeah, the reason why we're doing this, we can take the square root of 25 and 9 and 4. That's going to help us simplify that. Now it's a good part. We can cross this stuff out. So we're going to cross out 25 and put a what, folks? And the 3x, I can't do anything with that. That's not a perfect square. The power's less than the root here, so I'm going to get the square root of 3x. Minus, I do have a 3 out here being multiplied. That 3 is going to be there being multiplied by whatever else I get. Now the square root of 9 gives you, but again, I get a square root of 3x. Plus, square root of 4, I know that thing's 2. And lastly, I get a square root of 3x. What's the next thing we're supposed to do?
Multiply.
Yeah, we're going to multiply. Before we combine our like radicals, we are going to multiply. I want to make sure we get this number right, so we're not mistakenly subtracting 3 or 6 or something crazy. Okay? So of course we get our 5, square root of 3x. We get, how much does that give you? Yeah, good. We are multiplying here, right? Those are a multiplication problem. We have 5 square root of 3x, minus 9 square root of 3x, plus 2 square root of 3x. Can we combine all of them?
Yep.
Notice if we would have got one thing different, like if that was like a 2x or a 5x, we would have been able to combine the first two, but not the last one. We've seen a problem like that here before, I think yesterday we saw one. How much you can get? Square root of 3x. Okay, so that root doesn't change, just like terms don't change. We're just basically adding the coefficients to those things. And you said negative 2? Exactly. So negative 2, square root of 3x, that's your final answer, as far as you can go on that problem. So combining all this together, you get something that looks nothing like it, do you? Now, if you just look at those numbers, the coefficients of 1, negative 3, and 1, well, you're not going to get negative 2. If you look at this and add those together, you're certainly not going to get square root of 3x. So what you start with doesn't even come close to describing what you end with. You really have to do the simplification, then look at how to combine those. Okay, the next one, we're not dealing with a square root anymore, we're dealing with a cube root. So the way we're looking at this, we're going to try to find perfect, not squares, perfect cubes. So this problem actually tricks a lot of people. It's not meant to, but it does. Because you know what a lot of people do here? They go, oh, I don't have to deal with 81. And when I cross it out, it's going to give me a 9. See how they can fall in that habit though, right? It's not correct. I mean, the cube root of 81 is not 9. The square root of 81 is. Right? But we're not dealing with the square root. We're dealing with the cube root. So we're trying to look for a perfect cube that actually divides 81. So if you put 9 here, you just cross out and put 9. That's not the way to go. We're not dealing with the square root. Actually, what we have is a cube root of, let's talk about 81. Can you think of a number that you can take a cube root of that goes into 81? There's only a couple choices. There's 8, 27, 64. Which one? 27 times 3 gives 81. Now the x to the fourth. Can we simplify the x to the fourth? X to the what? Yeah. Yeah, that's going to work because I know the power now matches the root. Don't forget about this 3. Power now matches the root. This is still x to the fourth. We've done this several times now. Now let's work on the next one. How about this? How about that 3? Can I bring out that 3?
No.
Okay, so there's nothing I can do with that. Cube root of 3 is, I don't know, we're going to leave it. There's not a perfect cube that goes into that number besides 1, and 1 really doesn't help us out at all. X to the fourth, though, we're going to be able to do the same thing. We're going to do x cubed times x. So really, we're just simplifying like you did a couple homeworks ago, just that simplification process 2 times. Then we're looking to see if we're going to have any like radicals, and then we start adding or subtracting them. Okay, everybody, cube root of 27, what do we get?
3.
That's going to go outside the radical. Cube root of 3, what do we get?
Stays inside.
Okay, so I'm going to circle it. Anything I circle stays inside my root. Cube root of x cubed, what do we have? And the cube root of x?
Stays inside.
Oh, we're going to circle it. Okay. Don't forget that you do in fact have a cube root. You got to have that. What's left inside of my cube root?
3.
That's exactly what we have circled, right? What we couldn't take out, what we couldn't simplify, we leave. Now over here, we have a different situation. We don't have any numbers that can pull out of our root. All we have is a 3, which we can't do anything with. We've got an x cubed, which we can. That gives you an x, but then we have an x which we can't do anything with. So inside of the radical, you have a cube root of 3x again. So we've simplified pretty much 2 problems in 1. We know how to do this pretty well. We know how to do this pretty well. And now we're looking to see if we can add or subtract these. Can you add those together?
Yep. 4x.
Yeah, we have exactly the same thing here. We have the same like terms. We have an x and an x to the first power. Cube root, 3x is a radicand. It's identical except for the coefficients. That's what we want to have happen. That's how we combine like terms, or in this case like radicals. We have a coefficient of 3, we have a coefficient of 1. So when you add those together, you should be getting 4 out of that. So this does count for something. So 4x, cube root of 3x. That's your final answer as far as you can go. Raise your hand if you feel okay with this so far. Okay, good, all right. Now, you know I was going to do it to you. How do you deal with some fractions? How do you deal with some fractions? Oh my. Can you deal with fractions?
Yep.
Sure, and you basically just subtract fractions, right? What do you need in order to add or subtract fractions? Great, yeah, you need one. Now, before you rush off and go ahead and find your common denominator, what I'd like you to do is simplify your radicals first. Okay, this is not the same thing as what we did yesterday where we combined our radicals because there's no radicals on the denominator. Otherwise, that's exactly what we would be doing. Are you with me on that? If you have those 2 radicals, sure, combine them first. If you don't, in this case we have a radical here, no radical here. We can't combine them. There's nothing to combine. Radical here, no radical here. There's nothing to combine. Okay, if there were 2 radicals, absolutely, you would make that one radical first and try to simplify your fractions. Right here, what you can't do, you cannot combine this under one radical because that one doesn't even have a radical. Imagine if you're right with that. So in this case, yeah, we're certainly going to simplify these roots. Well, this one we can't, but the square root of 75, we actually did that earlier in this class today. That's going to be, if you think about that, that's 25 times 3, that's 5 root 3. You with me on that? So we're going to simplify that as 5 root 3. Five root 3 over 9 minus root 3 over 2. If you're not getting 5 root 3, this is the 25 times 3. We take the square root of 25, that gives you the 5, and then we have the root 3. So do this step, we've done that a couple times. Make sure we can get 5 root 3 out of that. Am I okay to add or subtract these now? Okay, so let's think on our own. Don't say it out loud, but think of the common denominator you're going to have. What is the common denominator?
18.
Okay. And just like you added and subtracted fractions in pre-algebra, teaching that right now in another class, how to do exactly this. What do you do in order to get 18?
Multiply the first fraction by 2 and multiply.
Wait, just 2? Like that?
2 over 2.
Okay, what we're really doing is multiplying by 1, right? Just doing it in a very fancy way. 2 over 2 still makes 1. That means you're changing not the value of the function, just the way it looks. We're purposely unsimplifying this fraction so as to get a common denominator. That's what we do. So 2 over, not 2. Sorry, I said 1 and I wrote 1. I meant 2 over 2 gives you 1. Hopefully you didn't write down the 1. That was the wrong thing to do. 2 over 2 here, and here we're getting what?
99.
Yeah, that's going to give us 18, 18, exactly what we want it to be. So we're going to have to multiply these things. I want you to look back up here. We talked about this earlier. When you multiply 2 times 5 root 3, do you multiply the 2 times the 5, the 2 times the 3, or both the 2 times the 5 and the 2 times the 3? Not the 3? No, it's like multiplying 2 times 5x. You just do 2 times 5, and then you have the x, very much like a like term, okay? Or with a variable. So we would get 10 root 3, not 10 root 6, not 10 root 6, over 18, and then minus 9 root 3. Notice this. I want you to really pay attention because I'm going to talk about this in about maybe 10, let me jump in. When you're doing the root 3 times 9, do you notice that we don't get root 27? Do you guys see what I'm talking about? In order to get root 27, you'd have to have a square root around that thing. That would give you square root 27. We talked about that, right? That's using the product rule, putting together roots. In order to put together roots and get root 27, well, you have to have both of them being roots. Otherwise, if you don't, like we don't here, this is like x times 9. You're getting 9x. You put the 9 in front, you have 9 root 3 in this case, over 18. That's the way we deal. That's the way we deal with these fractions. Hey, now that we have a common denominator, what common denominators say is that you're going to combine your fractions. Your denominator is going to be how much? Yeah, when we add or subtract, we don't change the denominator. On the numerator, we do it just like any other fractions. We have our first numerator, whatever that sign is, our second numerator, and then we try to simplify. Can you combine those roots? So we got 10 root 3 minus 9 root 3. Do we have the same root?
Yep.
Do we have the same radicand?
Yep.
Because you combine them. We just do 10 minus 9, how much do you get?
1.
1 what?
Root 3.
So we're going to get root 3 over 8. We don't have to put the 1, it's like saying 1x. But we would get 1 root 3. So we're going to put root 3 over 18. Notice how simplifying your radical here really helped you. Already had a common radical. That way you just multiply your numbers, your coefficients, and that really helps. Okay? Otherwise, you're going to have to simplify this at some point. Somewhere you're going to have to do that. So I know it's confusing. The first thing we did when we had a radical over a radical, we didn't simplify first, we combined them first. That's always what you do when you have a radical over a radical. However, if you don't, then sure, go ahead and simplify that because there's nothing you're going to have to combine later. It's just that one root. How do you feel all right with this so far? Okay, one last question for you. Can I simplify this and get square root of 1 over 6? Does that work?
No.
Square root of 1? Yes, please. I like it. No shortage here. 1 over 6? Simplify this and get square root of 1 over 6. Does that work?
No.
Square root of 1 over, can I just go 1 over 6?
No.
If I had a root over a root, sure, I could combine them, and that would make that fraction, but I don't. Okay, so I cannot just simplify within a root unless I have
Okay. I had like a completely fundamental flaw in my math. I could not do radicals at all. I literally just did not know. I know everything about radicals now. I've gotten every single question right, other than like forgetting some roots and some exponent stuff. But I got those like two instances. I got this all down basically. I'll do this as part of my aggregate review of roots and adding them, subtracting them, multiplying them, dividing them. But no, I'm pretty good on it actually, so I don't think I have to go back to it. I think tomorrow I'm going to go back to logs, not logs. I'm going to go back to rational expressions, and then half rational expressions, half logs, and then get those down, especially logs. Uh, yeah, we'll go from there.